Welcome everyone to our last session for the day, but this will be a very long session. It goes from now all the way till 4 o'clock. So we have a long list of presenters, basically nine of the experimenters that will be presenting their work. And really, there are three types of people here today with us. There are early users of Fabric that has been onboarded some time for now, and then they're working with the very limited Fabric environment so far, trying to analyze the environment and get some early setup for their experiments. There are the second type of people are really actively integrating their experiment components that are beyond Fabric, so onboarding their system, their infrastructure applications. And then lastly, so we have Miriam Leeser from Northeastern today, who is really in the category of developing features that experimenters will be anticipating. And that's particularly on the FPGA with some of the P4 functionalities that everyone has been talking about. So in that spirit, we did not want to sort of separate this into different chunks of data of talks, but rather we lined them all up. Hopefully, that will continue to merge and evolve into a conversation that speaks to each other. So with that, I will just follow this list of this order that I have in front of me to go through the presentation. And the first one will be Yixin Sun. Yixin is one of our Fabric science design drivers that have been with the project from the get-go from University of Virginia. So Yixin, you wanted to first talk about your experiments?
Sure. I think, I mean, I can
I
share my
will,
screen.
yes.
Yeah.
Yep,
Okay.
please.
Awesome. Thank you. Okay. And all right. So assuming that you can all see my screen and hear me, and so again, thanks, Casey, for the introduction. So my name is Yixin, and I'm an assistant professor at the University of Virginia. First, I guess before kind of I get into how I plan to use Fabric for my experiments, so overall, a large body of my research has been focusing on routing security, and therefore I've done a lot of control plane experiments, mostly using Turing testbed in the past, on especially kind of the implication of routing security, or rather insecurity, on critical internet applications. So kind of part of the routing security topic has actually been covered by Ethan in the last session. So I'll kind of just briefly go through it. So routing is notoriously insecure, especially talking about BGP. So the one thing that Ethan has mentioned was the lack of mechanism to verify the correctness of the path or the origin. So a lot of the existing efforts or to secure routing have been focused on achieving origin validation, like RPKI, right? Kind of validating the owner of a prefix. But then origin validation is still insufficient to prevent more sophisticated attacks that basically manipulate the path, not just the origin. So proposals that further provide path security, like BGP-SEG, have been proposed, but as we know, it requires significant changes to the existing routing infrastructure, and has yet to see any production deployment. And then on the other hand, there's all these private backbones, new internet architectures like Cyan, which have also been proposed, which I'll talk about more next. So that's kind of number one, lack of mechanism to verify the correctness of the path. And so another thing that I want to highlight, which is the second bullet point here, lack of transparency. So this is kind of looking at the routing security problem through another perspective, which is essentially, to some degree, all these different solutions are developing mechanisms to share the ground truth knowledge about which path or which origin should be correct, right? Say, for example, very basic things like different defensive filtering mechanisms, like prefix filtering. It's basically like a customer sharing their ground truth knowledge with the provider, and therefore the provider can implement filters to filter the announcement from the customers, or like say in the peer locking case, it's basically knowledge sharing among a group of peers. But these kind of sharing are kind of local, like on a local scale. On the other hand, kind of if we look at RPKI from this angle, it's basically kind of sharing of this routing ground truth knowledge in a centralized database that's kind of shared globally. So this is kind of another look at these issues. If we could have sufficient and reliable transparency about routing knowledge, it could, in some sense, provide better routing security. So I will also talk more about it in terms of like new designs and experiments that we do to try to improve routing transparency to kind of help with routing security in the end. So that's kind of the two angles that I've focused on recently in ongoing and upcoming experiments. And so specifically kind of tying to Fabric, because I mean, for these controlled plan experiments, it's very helpful to actually kind of be able to make announcements, test whatever mechanisms we build in the wild. So previously, we've been using Purine testbed a lot, but I'm very kind of grateful to see this kind of Purine/Fabric integration, which basically enables us to do larger scale experiments. For example, Fabric could provide a connection to Internet 2/ESNet to kind of carry out future experiments. And so next, I will talk about the first experiment that we're doing called Secure Backbone AS, or we call it SBAS. And so the intuitions so kind of going back to the lack of mechanism to provide path security. So Cyan is one of the clean slate internet architectures that have many interesting security properties along with other ones. And but the issue is that you can only get the security benefits within Cyan. So it's kind of like an isolated island. It doesn't really benefit the rest of the internet. So our kind of thinking is, can we develop a new mechanism architecture to basically bridge this gap and integrate this secure routing backbone, which is Cyan, with the current internet? And so here's, oops. Sorry. Oh. I think I clicked the wrong button, but sorry, I'll start sharing again. Okay. Okay, here we go. Yeah, here. So this is the original Cyan, right? A kind of backbone architecture on its own. And so what we're essentially doing is, so say we're gonna build, oops, no. All right, I might just do this. Okay, cool. Yeah, so this is Cyan. And so within Cyan, so we put together this aspect, which is basically adding these points of presence at the edge of Cyan. And then so these pops basically serve as the main bridge between the Cyan world and the outside world. And so among the pops, it's basically iBGP sessions over Cyan to coordinate among them. And so in some sense, this Cyan topology is basically a secure full mesh between the pops. And so towards the outside world, these aspects will be making BGP announcements, acting from like a single AS number assigned to it. So we do have an AS number for ourselves, which we're using or will be using to make BGP announcements. And so here, it's basically kind of, this is the connection that we were using peering, and we will be using Fabric/peering going forward to basically making just regular BGP announcements, but through our SBAS AS number. And this connection, so previously we used different peering sites, and I guess through Fabric, this will potentially go out to Internet 2 and ESNet. We're also adding other providers, for example, like Vultr, to kind of to announce our prefix and our routes. And okay, so this is the announcement part. And finally, say if there's a customer who want to use our SBAS to improve their routing security, they basically can establish a secure VPN tunnel to one of the POPs, well, depending on where they're located. And then, so then they can have their basically their own prefix redistributed through this secure backbone SBAS and reach other parts of the internet. And so as an example, oops, now it pops up again. Okay, here. So as an example, let's say ASA here is the customer and who wants to use SBAS. And this announcement is basically first being sent to SBAS, and then SBAS is gonna kind of redistribute the route to like all the other links, say Internet 2, ESNet, or Vultr, or other providers that we can peer with. And then say from another client's point of view, say this could be just any other regular machine on the internet. This client is basically gonna be receiving this announcement through, well, just like a regular BGP announcement. And another thing is distributing the routes through SBAS doesn't prevent this customer AS from announcing the route somewhere else. So for example, this ASA could still be announcing the route from like just, regular, like how it would have done without using SBAS through another provider or peers and etc. So basically from the client's point of view, the client does not need to be aware of SBAS or Cyan. It's just kind of, it would be doing what it's already doing without actually being aware of the service. And so the client's traffic is attracted by SBAS, just like, just regular BGP routing policies and etc. And of course, in order to attract more client traffic, who are not aware of SBAS or Cyan, we need to have a lot of like POPs. And so here, let's say, hypothetically speaking, the client would be kind of preferring to route traffic through this POP/SBAS because it's only like one hop away, or potentially integrating other kind of routing preferences and etc. And so this is kind of like one neat feature of this backbone that we're developing, that the client invisibly is kind of having enhanced routing security properties without even like changing anything or being aware of it. But on the other hand, this ASA, the original AS who's redistributing the route, this AS needs to, participate. And so this is one experiment that that's currently going on, and we do plan to kind of bring it to Fabric and basically run it at a larger scale. And so I guess I'm probably running low on time. So I will quickly go through the other experiment that we're kind of currently doing and planning to expand in the future. So this is kind of looking at the other angle, which is how can we improve routing transparency, right? Because a lot of the times, like these ASAs and routers, they have their own local knowledge, but which is not shared with others, and therefore sometimes attacks happen that's only visible to local area, or like and others. It's hard for others to tell whether it's legit or it's actually an attack. So what we're thinking about is actually using BGP communities to share additional routing information about either the origin or the path. And so the intuition is that, yes, for example, for origin validation, we have RPKI and stuff, but still, as of now, the majority of the ASs do not have ROA records. On the other hand, the kind of status quo is like you provide a letter of authorization, you give it to your provider, and then they're good. But then this verification step, which is an LOA, is actually not known to others. So can we make this knowledge or share this knowledge with others, at least to kind of provide some sort of confidence or informal validation in terms of like the route that's actually being announced. Like the origin actually has gone through this LLA type of validation. So this is kind of one example of additional information that could be shared that's not currently covered by things like RPKI. And another aspect of this, if we're talking about BGP communities, the community itself is actually not secure. So there's like a whole the whole area of research could be how can we secure BGP communities from the perspective, like how can we monitor it? How should ASs set filters on the communities? And is there any possibility of adding any sort of authentication to the community itself? So this is some kind of like a future work that we're planning. So as of now, so we've been kind of mostly doing measurements on communities, especially large BGP communities, including controlled experiment over the peering testbed. But on the other hand, I think this integration of Fabric/peering would allow us to do kind of more controlled experiments, measurements on this front. Yeah, so I think that's probably about time for me, and that's my presentation about like 2 kinds of experiments that we're planning to do. And yeah, thank you.
Great, thank you, Yixin. So the next talk will be Russ Clark from Georgia Tech. Russ is also one of our science design drivers, have been looking from the IoT perspective. Russ, will you be sharing your slides?
Yes. First, we want to see if we can promote our student,
yes.
Fu.
We'll have Fu Shen also come join the stage.
So I just invited Fu Shen up, so you should be able to join. Oh, it's actually, we're still maxed out on people, so I'll work with that. Maybe.
All right. I'll go ahead and get started, and
sounds good.
Pick us up on slide 4. All right, that looks right. Hello, everybody. Russ Clark, Georgia Tech. My colleague Matt Sanders and I are leading an effort here to basically bring our sensor work, our smart sea level sensor project in particular, to Fabric, and we've sort of rethought that and what that means to, over the last several months, and now looking more specifically at what does it mean to bring LoRaWAN capabilities and IoT in general to Fabric, both for doing experimentations that we want to do on resiliency, but also perhaps as a general resource for Fabric. So I'll be presenting today with one of our students, Fu Shen. We've had the opportunity over the last several months for several students here at Tech to start working with Fabric, first the beta sites and now moving to production. Kicking the tires, as they say, learning to work through some of the tutorials, the Jupyter notebooks and what have you. And really thrilled that Jack Locke from Boston has been able to join us thanks to Paul's recommendation. Jack is one of the students that worked, one of the early adopter students that presented earlier, and has been super supportive and met with us several times and basically helped us work through some of the early adopter issues we've had. So super thankful to Jack's support as well. So what are we all about? What are we trying to do? I'll do that introduction here. We are motivated by this use case of environmental sensors primarily. In our case, the Smart Sea Level Sensors project, a number of sensors on the Georgia coast that are monitoring water level, storm surge, sea level rise. and it's a very high density network of these low cost sensors based on LoRaWAN. And the way all of this architecture connects to the world is through the Things Network software architecture. The details of which are this implementation known as the Things Stack that's depicted here, and then a whole bunch of applications on the right that they're consuming that data for various reasons, from sort of real-time emergency response to modeling and forecasting. And in some way, what we're about with this project now is sort of taking this box in the middle, this collection of boxes in the middle, and tearing them apart and figuring out what's the right way to deploy these on Fabric. What's the right way to leverage Fabric for sort of rethinking about how this architecture works, how we can make it more resilient, perhaps, but more perhaps also how can we make it available to the larger Fabric community. Primarily, we're about looking at these architectures to improve resiliency, especially for network partition events. During the storm that we're the hurricane that we're all about trying to support, and re-architecting things to understand that. This is a slight advancement, if you will, and tweak of the architecture we presented back in May that at the time was proposed architecture, and we're starting to make a little more progress on that. But basically what we want to do is map all of these different sensor sources on the Georgia coast to this Things Stack architecture deployed across Fabric, and ultimately have both live sensor feeds as well as stored sensor data archives that we can replay. And with that, if Fu is now available, I will turn it over to her to tell you about what we've actually been doing with our beta testing in the last couple of months. There she is.
Hello everyone. Let me turn on my camera. Hello everybody. I am Fu. Here I am going to give a high-level brief overview of our phase 1 experiment. So as what we can see at the first slides, this is the Things Stack setup, install, or we say configuration and installation on the Fabric platform. The top left screen figure is basically a very generic use cases, just requesting a slices. As we get the management IP back, we will be continue using that IP address to accomplish our configuration and installation. Again, so all this experiment has been done under the beta. So as what we can see at the second figure, which is the left bottom part, is we were using the direct access to the node. We are on our process of migrating to the production, so this will be replacing by the jump host connection once we finish the migrate. Completed our migration. And the figure on the right side is basically the minimum required configuration and installation to be able to spin up the Things Stack server on Fabric. So the Things Stack provides a very good Docker compose file which allows us to easily pull all the image and accomplish all the configuration. So to be able to do that, we would have to have the Docker and Docker compose correctly installed. We would be able to download those at least 2 of the configuration files, either from the Things Stack or from your local repository. So there's a lot of the configuration would be specified towards your infrastructure. So this is one of the part, like how you define your host. This is the basic the entry point of how you would like the Things Stack to be spun up on the fabric. And once we get that configuration sorted out, we will be able to pull out the image, passing a couple of additional configuration to set up the command line interfaces, the console interfaces, and then once we are bringing up the Docker Compose, we will be able to see a list of the port that the sync stack is listening to, and also we will be able to see the nice console that the sync stacks provide us. So this is at this point, we have complete all the initial installation of the sync stack service on the Fabric platform. Next, we will move to the gateway setup. So for this page, as we will see, these pictures highlighted the basic configuration that required for the gateway. So as we will see, the server address here is the IP address. If we still remember the number that from the last slide, that's the IP address of the management IP of the slice that we requested. So that's the most important part. And also besides that, we would have to make sure we configure the right bandwidth and choose the right channel plan for our gateway, which is shown on the right-hand side. Once we get this gateway setup, we will be able to add this gateway to the sync stack server that we have been running on Fabric. So next slide, we will be able to show some of the verifications. So for the current stage, to be able to access to the console, we would have to do a tunneling. Again, like the top tunneling is using the was pointing to the the beta version, beta Fabric. So we will be updating it, and eventually we would love to see in the future we are able to actually have this nice console GUI facing to the public. So the figure here we are seeing, which having the traffic going through the tunneling to the management IP, is the sync stack that have connected to the gateway that we set up earlier and polling the live data. And all these servers been running on the Fabric, and we would love to see in the future. This is basically a setup for the one of the nodes that we have seen in the topology picture, and in the future plan, we would love to bring it up to the other nodes and have all the basically the networks working, so we would be able to explore our approach to resolve the resilient issues. So for the next slide, I am going to share a little bit of the experience and the feedbacks that we have collected from the team. Which is a great appreciation to the Fabric team, which we have received a lot of support and swift response from the team. And also special thanks to Jack, as Russ mentioned earlier, that he's one of the Fabric student teams who's from Boston University, which joined our team to help us to be on board to the Fabric platform. So for our current experiment, there's a couple of the improvements we would love to make for our next phase. First of all, like we would love to definitely, once we move to the production, we would love to replacing the ragged access with jump hosts for the increased security. And also so for the installation that we've seen for the sync stack, which comes with a database and a Redis caching system. So everything we have seen, the installation we've seen so far from the previous slides, not persistent yet. So for the next phase, we will love to bring in the persistent customized the database and caching system, so we would be able to keep the data and some of the configurations. So also we would love to add HTTP as certificate configuration for the security. Once we would love to once we are able to make it open to the public. And there's also some of the features we would love to see, which I think some of those has been answered during the previous session already. So we will so one of the major things we would love to see is to be able to enabling the public-facing network, which that was exciting when we were hearing there was some of the progress about this part. And another really great suggestion we've collected from the team is we would love to. So for now, we can see from the Fabric knowledge base page, we would be able to see there's a status availability as the clusters. As a whole cluster to see whether it's available or not. And I think a lot of us would love to see some of the a more in detailed availability as when we go explore more about the resiliency and availability. This would be a great info page for us. And also another suggestion we collected from team is to see if there's a way that we can save the basic configuration of our installation to something like a Docker image or some related configuration, so that we can easily retrieve all the settings, all the configurations and installations whenever we bring up a new slice and new nodes. And also the next one is, as we mentioned, is the enabling the public-facing network, and that would be, and we're excited about the next experiments we're going to have.
Right.
And yeah, so here we are here to take if we have any question, then we would love to answer.
Yeah.
Right,
thank you.
Yeah, thank you, Fu. Let me
No
just say one more thing, and I'll pass it back to you, Casey. We're also very interested and would love feedback from the community about what sort of features, what capabilities of what would it mean to add LoRaWAN and sensor network to Fabric for you, right? What do you think? What are the most important things you would want to be able to do? Because that's part of what we're wrestling a bit with is, so what is in fact the right service to ultimately be created? And there's probably 3 or 4 different answers to that we're working through. So would appreciate any comments and suggestions along those ways. But with that, I'll stop sharing and we'll hand it off to the next presenter.
Absolutely. Well, thank you, Russ. Thank you, Fu. So this is really a very new nature of experiments that's happening with IoT and LoRaWAN. So absolutely, please continue the conversation with the community. Next up, Alex Feltus from Clemson. And I believe you'll also be talking on behalf of Alex from FIU, right?
A little bit.
A little bit, okay. But yeah, Alex, feel free to kick yours off.
Okay. Can you see it?
Yep.
Okay, so yeah, so mine's probably is extremely vapor right now, just to let you know. But this is so I'm Alex Feltus at Clemson University. I'm a biologist. I do computational biology, and we deal with huge data sets. And we are going to the whole point of this, I guess, is that we're going to make a data lake on Fabric where we can load it up with all the genomes that have ever been sequenced, that have been pre-processed, and then they can be accessed via a named data networking strategy where we have all the data named and then pulled into workflows outside of Fabric. So we're going to be pulling data into the Open Science Grid and the Pacific Research Platform are 2 primary places where we'll be pulling data. And this is a collaboration. This was funded recently, I think back in October, by the NSF under a grant to Susmit Shanigrahi from Tennessee Tech, but it's also a collaboration with FIU and UCLA and I'm at Clemson. And this is a list of people that have worked on the project really for a couple of years at different aspects of it. And so this is what I've done on Fabric. I've created a project and I ran a Jupyter notebook. That's about as far as I've gotten. But after the finals are over this week, it's going to start picking up a lot of steam. But what this is motivated by is essentially this data lake is that there's tons of data out there. There's over 60 petabytes of data that you can access from one archive right now. And it's SRA. Most of this data, I guess all this data is stored in the cloud right now that we can pull and pull parts of it, aggregate into our data lake. This is representing over data from over 512,000 species now on the planet is in these databases. So we have lots of these data sources, or this is one data source. But the problem is that people want to do lots of experiments and aggregate data from different repositories. So I just showed you one with 60 petabytes, but they're all over the place. They're all over the world. And some of them are stuck in local hard drives and things like that. And so want to be able to get this data and access it. We want to access it by name, because if you want to find the data right now, you have to be bioinformatics is one of the things that I do, is to be able to search databases and understand what the data sets are to be able to aggregate them in the first place. So we want to be able to solve this problem where if you are able to find the data, get it out into the data lake and transfer it abstracted from the end user, so we can use how you pull things from buckets and different weird access places, like using Aspera from NCBI and different data transfer mechanisms, be able to have all this data named in the data lake, so that people can just access it through a naming strategy from our name data networking strategy. And so really what this is to me is that as a biologist, as the end user, I'm trying to make this FAIR data more fair, I guess, because right now it's fair. It's findable, accessible, interoperable through different data formats, and reusable. But you have to be like a genius, or actually not even a genius. You have to have been working in this field for 20 years like me to even know how to find this stuff a lot of times. This is a big part of what I teach in my classes. And so students can go and say, I've got this really cool hypothesis. I'm going to go ask the lake for the data that I want. This is what we want to install in Fabric. This is I'm going to black box this seriously, because Alex was supposed to be here and give more details with this. And it's an emerging product we're making right now. It's called Hydra. This is a solution to that problem, a name data networking distributed repo. And again, this is a layer for me. It's a named layer where you can get the data. It's abstracting a lot of that back end stuff from the user. And these data sets, again, are huge. So we need something like Fabric that's got really shiny hardware to be able to move stuff around quickly. And so it's again, one aspect is Hydra's this fair layer adapter to be able to get the data, but it's got all the back end end-to-end features like caching and security and things like that. And that's what I'll black box, because I will definitely screw it up. But there is a paper that we have published recently. Here the slide deck is in the should be up with everybody else. And we're developing repos and things like that. In my lab, we've been able to actually create a data lake on the Pacific Research Platform, a Kubernetes cluster that's distributed. And we're able to do that by running containers inside VMs. I won't go into the details with that, but we'll probably have the same kind of architecture once a lot of the Hydra is designed, or even some precursors to it, to deploy onto a Fabric. We're actually ready to deploy some prototypes right now. Again, with name data networking, instead of using IP addresses to move data around, this does fetch it by name. So we publish data, a registry of names, and be able to actually pull data from the network directly using things like Homo sapiens genome version, GRC H38 or whatever the names we're using. Fortunately, with biology is as complicated as it gets, right? Because it's the product of billions of years of randomness. But there is an organization to biology. It's organized evolutionarily. So all of our names are built around the tree of life. And so we have different taxons, different names that are already there for organisms. Like here's an armadillo, different levels of organisms. Here's human. There's Homo sapiens down here, genus and species. So we can relate a lot of the data at different levels here in a user, a UI, to be able to find the data you want and find the name that's actually out in the end-to-end system. We've gone through a lot. This is a paper we published recently. We've gone through and have all of our naming strategies there. We have our genomes index. We have a lot of back-end software like Pinome software from Washington State University that pulls all genomes that exist today and pre-processes them. You get terabytes of data like this. And this is a challenging thing for people to do, this pre-processing step, and loading these pre-processed named genomes in the data lake. And this is, again, the experimental design right now. And if anybody can read this fast and give me any red flags up front, I'll find them out pretty soon. But our idea here is to provision, several Fabric nodes. I have 3 here because I think that was the beta that we're trying to do. But get 5, 10 nodes. We'll scale up. Fabric nodes on top of VLAN, be able to then have the data, the nodes hold a lot of data, so we have storage issues. So we want to be able to use fast data storage formats, right, and whatever we can scale up. We want to then deploy Hydra, and probably some precursors to that is this genome data lake. And then what we'll deploy that, and we'll be able to compare, different topologies, latencies, and moving data around in the data lake. And we'll publish kind of a set of 300 genomes that we have that are a pretty big data set, and some different like kidney data sets and some rice that you eat data sets that are different scales, and we'll plug them out there and pull them out of the data lake into workflows, and we'll do lots of performance evaluations and learn how much replication do we have of data, like do some really basic experiments. And we'll have we have a web service already to be able to find the name and pull data from this test bed. And the idea here is that, and this is a big part of what Clemson is doing in this project, is I'm going to be provisioning. We have the ability to provision random nodes on the Pacific Research Platform. We could also do this on OSG, I'm sure, and then pull from there, at different geographies, right, and different topologies, and run the same workflow over and over and over again. And we have lots of using the Nextflow Workflow Manager, we have tools to be able to monitor our research patterns and be able to model, if we change topologies, we can actually model and predict if we'll get performance increases and stuff. This is all like an end user side of things. And I just said all those things, I guess, but lots of metrics that we'll be able to do. So our goal here, and this is part of the NSF project that we have, is to simulate users on OSG and or Pacific Research Platform, or maybe even other systems, to be pulling data from the lake, and then try to see how fast we can do it, right? And if the performance boosts performance, if it's good, I could see 5 years from now writing a grant to make a production data lake to store all the genomes on, which is a service that most biologists need to be able to do a lot of their genomic work. I have no idea how long I was. I'll stop right there.
All right, thank you, Alex. Just one curiosity. I think you're assuming that you broadly connect to the internet to implement your data lake. So Ilya brought out today one important consideration is we only support IPv6 when interfacing with internet. So that's something that perhaps down the road we can discuss.
I think we probably should discuss that, yes.
Right. All right. So the next up will be Rob Gardner. Rob will be talking about a very, very active effort going on integrating Stern's workflow all the way to the US. Rob?
Yeah. Hey, everybody. Glad to be here today and tell you about the work we're doing here. This is essentially our setup that we have in mind sometime early next year. This is part of the FAB project. This is extension of Fabric internationally. So as Paul and Ilya already mentioned, we have a node that we're going to be building at CERN, a Fabric node there. And essentially the idea here is to quickly grab data out of CERN and bring it directly into an analysis environment over here on the left. So this is part of the ATLAS experiment at CERN. So this is one of the Large Hadron Collider experiments. In the US, we have about 500 active physicists on this project and 200 graduate students. And we have 3 analysis facilities distributed across the US, one at SLAC, Stanford, one at Brookhaven National Laboratory, and one that we're just starting here at University of Chicago. We want to investigate different ways that we can put capabilities into the network to speed up this process of delivery of data into analysis environments. And so we're exploring how we're going to, where we're going to place these services and how we're going to use them from different where we execute the workflows, for example. And so we thought it would be good to drive this with a demonstrator where we mimic basically a Higgs boson search at CERN and just explore a little bit how Fab and Fabric can speed things up. Here we're not doing we're not using the actual Atlas experimental data, but we're using open data. So it's a smaller subset of the data and sort of allowed to sort of use in open environments. And then we, in the middle here, we use this service here, which is pulling data and reformatting it. It's called Service X, and it's part of the IRIS-HEP project, which is developed within the IRIS-HEP project, which is NSF Software Institute for Innovation in Software in High Energy Physics. And again, as I mentioned, we want to deliver this data to an analysis facility at UChicago. We can actually, this will be very flexible when we do this. These facilities can sort of be anywhere. And then we are hooking up with processing frameworks also being developed in IRIS-HEP. So one is called Coffee at Casa, and I'll show you what this all looks like when it's put together. So what is Service X? So this is essentially a service which can sit either close to the processing system, or it can sit close to the data source. In this case, in this experiment, we're mimicking placing this at CERN. And essentially what it does is it gives end user physicists nearly interactive access to data, very large scale data sets, by putting up a filtering layer in between and an acceleration layer in between. And one of the other themes here is to sort of get the data into a format that the end user physicists can quickly use, in a modern processing framework, run out of a Jupyter notebook, for example. So there is data access issues here. There are filtering issues. There are reformatting issues, taking it out of the native format and putting it into the columnar arrays that the Python tools are using. And for that, we have a design Service X to be this collection of microservices that can be flexibly run on a Kubernetes infrastructure. So there are links here. And I wanted to just mention that within IRIS-HEP, we're using these kinds of demonstrators or challenge problems to help us define our path. And so there is a workshop here that we recently had where we're looking at the first versions of the future analysis pipelines that'll be used in high energy physics. So we need Kubernetes on Fabric. And I should also mention here that on the title slide, which I skipped over very quickly, are all the folks that are doing this work. So this is the collection of work from my colleagues at Michigan, Utah, and Chicago, part of the SLATE project, for example, part of IRIS-HEP, part of the US Atlas Computing Operations Program, sort of a lot of different players from different projects sort of contributing here into this approach here. So this one is about, I have a couple of slides here about just getting Kubernetes as our, platform, onto the Fabric infrastructure, which makes things much easier for us than downstream. And I won't go through this in too much detail, except to note that it's, again, using the Jupyter Notebook interface. It uses a couple of Jupyter Notebooks, so it does this in a two-step process. The various files are given to a CubeSpray deployment, which actually, as part of the SLATE project, we prototyped on Chameleon. But essentially, you're just going to get Kubernetes there and then register that little cluster into the SLATE Federation, which gives us other tools for handling the software environment and controlling policy, which I'll say a little bit about. This is what it looks like then on Fabric. So what we've done is generated a slice on the NCSA site. We chose NCSA because it's sort of in the neighborhood. We're hoping that it's actually in the same science DMZ as our analysis facility. We haven't actually done a highly granular network path verification, but we have other LHC resources at NCSA, and they're likely using the same network paths here. So we just didn't want to have to deal with that. So this is when it comes out of the Fabric environment and goes off into another infrastructure. And so we got the slice created. We do need to think a lot about how we monitor things once they're there. we wouldn't necessarily put a full-blown Prometheus type thing there to, at least in these initial tests, but we did put a little bit of monitoring there just to sort of see that the service is alive and responding. This is actually what the ServiceX quote unquote application looks like. It's a collection of microservices, and what you see over here are all of the things that are living in the Kubernetes cluster deployed on Fabric, and then so it reaches out to an end user out here, which is running a Jupyter notebook on a facility somewhere, and the queries within this notebook actually trigger the service inside Fabric to pull data from CERN and to reformat it and put it into a database that then can, an object database over here such that you can analyze it more later. So that's really not important here for this presentation, just to show you how we were able to assemble all these tools together. And it mentioned that we were using Slate as a, we typically deploy ServiceX, with Flux CD, and just do it directly there. But we're putting this into an image repository from an open container registry project that we're starting up this fall here called Soteria, hosted by Open Science Grid. So this is a way of getting sort of some added trust onto the applications that we're deploying on this infrastructure. And we're doing this sort of with an eye towards in the future when we deploy this at CERN. Some of the questions we first got from CERN IT was, what sort of policies are effective in place on the Fabric infrastructure there, since it's sitting on their, sitting on their network. And so we're using some of the other work that we had done with the container security and to help address some of those security and trust questions. So this is just a picture showing, for example, this is the container registry over here where we're putting ServiceX, the application, and then instead of pulling from Docker Hub, we're pulling from this more trustworthy source of data. So this is probably not important for necessarily just sort of quick tests that you would be doing on Fabric, but in the long run, we're thinking that we want to have a secure environment, and we want to be able to have some of the infrastructure, the trust and policy infrastructure in place to help us along that line as well. So the way this looks is that a physicist code running out of a Jupyter notebook basically embeds in the notebook clients which are calling out to the ServiceX service on Fabric, and it basically requests which data objects that it wants, applies any filters, and then prepares the data that it wants for downstream analysis as part of that. The ServiceX service spins up a number of things called transformers. So these are pods that are auto-scaled on Fabric. And the results that come back, so these are awkward arrays or Panda data frames, or this is a high-energy physics root file format, or sent to an object database on the analysis facility. And then the data is processed there sort of, with histograms and fitting and the end user. And then that can actually scale out. Actually, it can be done on a local, within a local process on the notebook, or it can be handed off to a DAS cluster, which is provided again by this Iris Hep service, Coffee at Casa. So this is what it looks like. This is just a snap, sort of a segment out of the notebook. And I just thought this was interesting because it just is pulling together all these different pieces of infrastructure and so forth inside an analysis that's ultimately going to lead to a physics plot. So over here is the open data source from CERN. This is ServiceX on the Fabric node at NCSA. These are queries designed by the physicist. This notebook is basically deployed on this analysis facility at Chicago, and all that comes together. And voila, over here, you're actually doing analysis of a Higgs boson decay to 2 Z's going to 4. These L's are called leptons. I know you guys are super interested in this, but these are basically is how actually Higgs boson is seen at CERN. And this just shows it all coming together in the nice plot here that the physicist would see. This is actually from a physicist's analysis, and it's really interesting here that you see that within the notebook, the data coming across in these various places where it's coming out of CERN through Fabric into the notebook. And there are links in here to the full set of notebooks, and actually you could actually run this yourself as well. So to summarize here, we've learned a bit about the Fabric interface, starting to use the portal, learning how to deploy Kubernetes. We successfully deployed a containerized application that's in active development in Iris HEP. For the LHC experiments, we've demonstrated this, on Fabric, doing data filtering, reformatting, and delivery into an external analysis set of clients. This is all, of course, at a very small scale. We're really looking forward to what this is going to look like. I mean, we have a number of technical issues really and obstacles here to overcome in terms of the network engineering that's going to have to happen between CERN and Service X and Fabric itself. We've got, we have to deal a little bit with I/O into and out of the Fabric itself. So there will be some traffic, there will be data moving around here, but, next year, this is what we're going to be learning. So, and that's all I got.
Thank you, Rob. Well, this is really encouraging. I think even though this is still going to scale up, but it sounds like you haven't seen any serious frictions of getting this rolled out.
No, I think that I'm really happy to see it all come together here. I mean, that was the idea, is that we wanted to see plots out of a notebook, with data coming through Fabric this way. And the approach that we're taking here is being able to take different parts of the service capability and move them around in the network. And so I think we've established we can do that pretty well on Fabric.
Awesome. Thank you, Rob. Next up, Hongxin Hu from University of Buffalo will be talking to us about the security experiments. Hongxin?
Yeah, can you hear me?
Yep.
Okay. Okay, good afternoon, everyone. So thanks, Casey, for invitation. I just want to talk about some our recent work about try to wrap some project, try to enable fast and scalable in network security, so within programmable switches. So here we mainly want to discuss how we can use maybe some Fabric features, especially Fabric provide programmable switch, and how those kinds maybe the environment can be used, to evaluate our recent projects. So here I will briefly discuss 3 research projects. So actually they are ongoing projects. We have some publications, but we still want to expand those ideas and design more comprehensive system. So especially we really need more maybe a comprehensive environment such like a Fabric can help us to evaluate those ideas, even those systems. And the first system we call IMAP. So this is the system. So actually they can achieve a fast and scalable in-network scanner. So using a programmable switch. So we recently presented the basic idea about this system in Hot Labs. The second system we call Facilitator. So in this system, actually we try to build a system. So we use program switch especially for DDoS attack defense. And the third system we call Fast FE. So in this system we try to accelerate machine learning. So especially deep learning based traffic analysis. So using programmable switches. So next I give you a brief overview for those 3 systems, and then we will discuss our kind of experiment setup, and I will also discuss how maybe Fabric can help us to build a more comprehensive experiment environment to evaluate our system. So we know network scanning. Network scanner is very important. So especially for our network environment. So we can use the scanner to find new vulnerabilities, even detect vulnerable hosts. Also, we can monitor the whole environment, the whole network, so we can identify services deployed in our network, in our environment. Currently, we have a couple existing network scanners, so such as Nmap, Zmap, even MassScan. But those existing scanners actually we implement in the servers. Also, we just run we run the packet processing using a CPU. We also just deploy them in the end host. So they can only provide a limited bandwidth. Also, if you want to test on the system, so there's a long scan passes. So to address those limitations, actually, so we propose we call in-network scanning. So the major idea, so we try to implement network scanners using program switches. So that's within switch. So we in that case we can deploy all those scanners in the network. So this can use the high bandwidth of network. Also, even we can do scanners, so we can achieve even short scan pass. So we have built a system we call IMAP. So in IMAP, so yeah, this diagram just shows the brief overview about our system. But more details, actually, you can, if you want to know more details, you can take a look at our paper. So the major ideas of we have implement the probe packet generating, so within a switch. Also, we also have response packet processing within a switch. So right now we just use very simple, only use one switch to evaluate our IMAP system. So we have plans to use Fabric to build maybe large scale environment, using this kind of large scale environment to evaluate IMAP in the future. So I will discuss a little bit later. The second system, so we have built actually, so our goal for this system, which we try to use program switch for DDoS attack defense. So we can see, so for today's DDoS defense system, so normally we put traffic scrambling center, so in the data center. So we use cloud-based mitigation mechanism. So actually, there are two solutions. One solution we use the mid boxes, for DDoS defense. So when you use the mid boxes, we can achieve high performance, but those mid boxes are very expensive. Also, they are inflexible. Another solution we try to use a network function virtualization, for DDoS defense. So we use NFV, so this can achieve flexible defense. Also, we can achieve elastic defense. But the major problems for NFV, because we implement those maximums using the hardware, use software, so they cannot achieve high performance. So to address those problems, so our ideas for precedence, we build a DDoS defense maxims within a program switches. So we have built the person languages, and we can specify some defense policy, and then so we can transfer those policies into the P4 languages, and we can enforce those policy DDoS defense policy within the program switches. So this diagram just shows the basic architecture for the precedent. So we have recently published paper also in the NDSS. So we also has done very limited experimental environment to evaluate our system. The third system, so we are building, so we try to address machine learning based security applications. Especially we try to address some deep learning based security network security applications. So actually we can see, so right now we have machine learning has been widely used for some network security applications, including bootleg detection, even website fingerprinting, even the coverage channel detection, even intrusion detection. So especially so recently, so deep learning has been widely used for those to build those systems. So when we use machine learning and deep learning, so actually there are two components for the system. One we call feature extractor, a lot of what we call behavior detector. So when we test, those existing system, maybe machine learning-based applications, there's one big problem. So they are not scalable. For today's the high speed, even large volume network traffic. So if I have a large volume traffic, actually no system the bootlet no system is actually in the bootlet in the feature extraction. So we have done, we can see we have done a very preliminary evaluation. So based on K-Suri. K-Suri is a deep learning based intrusion detection system. So we can see actually the feature extraction part we can see that they consume lots of CPU usage. So, but for behavior detection also consume CPU about 6% the CPU the usage, but I think the feature extraction is a major part. So they consume the performance on the feature extraction. So this is why so based on this kind of findings, so we build a system we call FastSFE. So in this system we just integrate the feature extraction part with the program within the program switch. So in this case, we also build policy languages, and even user can specify some policies for feature extraction. So those policies can be also enforced through the program switches, and then so we can try to make this kind of feature extraction faster. So we have present our preliminary result in the CCAM the workshop we call a span 1 year ago. So next we just want to discuss our kind of experimental setup. So our existing setup for those three systems, we just use one program switch. So to a P4 switch, and we just use two dial server so it's like, for example, for FastSFE, we use two dial server, one dial server for traffic generator, another dial server for backend server. Actually, so we really want to expand our experimental the environment. So we expand this environment can support at least three features. One is about programmable capability. So exactly, so we want to support is using the program switch to support those capabilities. Actually, three systems, so we use program switch to build high performance system. And the second feature we call in-network defense. So especially for IMAP and the precedence. So we really want to build security functions within the network, and then so we can do the in-network defense. And the third feature, exactly scalability and fast. They're very important. So we really want to build using a large scale system to evaluate our tools. Because for IMAP, so for IMAP, we really want to do right now we just use a very small scale test bed, but we really want to deploy this system and the user can make a large scale network to evaluate the efficiency of our system. Even for precedence, so right now we just do the defense using one switch and in the data center. So right now, the next step we want to build a distributed system. So we really want to see how distributed maybe the program switches, multiple program switches can help us to do DDoS defense, and then so mostly how we can build maybe a new system to allocate the different resources from the system. For FastSFE, so we want to build, especially for a deep learning based intrusion detection system, and then so we also want to use a large scale system to evaluate our system, our tool. So this is our plan. So we want to utilize the fabric to support those features. So because the fabric can provide programmable switches, so exactly so they can support the program capability for those systems. Also, fabric provide the in-network computer and storage. So this can be used for IMAP for precedent to evaluate the efficiency of the in-network defense. And the major feature for fabric is the large scale and high performance. So yeah, for our existing tools, we really want to use those features. We can build a large scale test bed and to test our system. Okay, I think I just discussed some our ongoing research and we have some plan to utilize the Fabric to support those projects.
Well, thank you very much, Hongxin. I think that's great that you gave 3 examples using P4 switching. And I think that's such a perfect continuation to the next talk. Miriam Leeser from Northeastern will talk to us about how Miriam is working with Fabric to enable P4 on our infrastructure. So Miriam, you want to share your slide?
Yeah, I'm just trying to. Are you seeing my slides?
Yes.
And you can hear me. Great. Yes.
Lovely.
So good afternoon, everybody. So yeah, my talk's a little different. So I'm actually looking at implementing P4 on FPGAs in different environments, including Fabric. So I wanted to say I love these workshops where there are other people who are like scientists who have problems they want to accelerate. I'm an FPGA person, and basically I like to take other people's applications and make them run faster. So it's kind of fun to hear from the biologists and the physicists about their problems, because I'm usually in FPGA workshops where all we're talking about is the hardware, basically. So this is very, very recent work, so I don't have a lot of details, so we're just getting started. So I have this NSF grant in collaboration with Michael Zink from UMass Amherst. And it's called PRATE, so P4 Research Enabled by Accelerators in National Testbeds. And we're looking at 4 different platforms that you've heard about during the day. So we're working with Chameleon, we're working with Cloud Lab. I actually have a NSF community infrastructure grant called Open Cloud Testbed, and that's what I'm most familiar with. So I'll talk a little bit about how we're going to support P4 there, and then obviously Fabric. And the idea behind these different platforms is the hardware setups are most likely going to be somewhat different, and the goals are also going to be somewhat different. So the hardware in this picture is probably old because I just cut and pasted this out of the proposal. But once again, the idea is to work with Cloud Lab, Chameleon, Fabric, and the Open Cloud Testbed. So the Open Cloud Testbed is an NSF size community research infrastructure grand project. And we're using Cloud Lab. I'll talk a little bit about that, and the Mass Open Cloud. And we've got 8 Alveo, Xilinx Alveo U280 FPGAs, which are kind of state-of-the-art data center systems. And we're putting 8 more online as soon as we can get the servers here. So, and then my understanding for Fabric is they're also going to be using some Xilinx FPGAs, but not the ones shown in this picture, probably something called an SN1000. Okay, so like I said, we've got in Open Cloud Testbed, we have soon to be 16 Xilinx FPGAs that are directly connected to 100 gig switches. So now I can do processing on my data straight off of the network rather than having extra hops to go through the host. And each FPGA has 200 gig connections to the switch. We're just starting to investigate P4. What we have played with is TCP, IP, and UDP stacks that run on the FPGAs. So once again, what you're avoiding is your data going through lots and lots of hops to get to the accelerator, but instead putting everything directly on the network. So we have a FPGA engineer working on the project who's developed a whole bunch of tutorials. I've put a couple links to GitHub to the tutorials. There's a UDP network demo, and there's a TCP IP network demo. So what Fabric is purchasing, my understanding, is something called an SN1000 card from Xilinx, which is specifically designed to be a SmartNIC, which is what the SN stands for. And it's the same family, so it's the same generation, very recent cards, but it's much more designed for networking, and particular P4 processing. So the technology families are very similar, but there are key differences. Specifically, the FPGAs, the SN1000s are likely going to be dedicated to P4 processing, with a small amount of user logic to do some add-on applications, whereas our goal in the open cloud testbed is really to have more space for big user applications side by side with supporting P4. So we're investigating both of those. They're similar technologies, but slightly different use models. And all of this is building off of both Xilinx hardware and software. So like I said, we're both of these systems, and I think Chameleon as well is going to be getting Xilinx FPGAs. And then we're going to look at doing P4 for FPGAs. And the first thing we're going to start with is it's called the Vitis Networking P4 stack, and see whether or not that suits our needs. There are actually other FPGA solutions to doing P4 programming. So if the Xilinx provided tools don't fit our needs, we'll be looking at other ones as well. But that's the basic idea, is to provide this directly on these FPGAs that are directly connected to the network, to enable the kinds of research that the person talking just in front of me was talking about. So basically doing that hardware accelerated FPGA without having to design your own ASIC. So this is a little bit about the open cloud testbed, and I'm putting it here because this we've been working on for a few years now, whereas the P4 stuff is relatively new. But this basically shows you the setup. So in the Mass Open Cloud, we're running the tools. So we provide a virtual machine, and in that virtual machine, we've set up all the tools you need from Xilinx to run things. And then we connect to Cloud Lab. So the development is done in Mass Open Cloud, and then the deployment / runtime is all done in Cloud Lab. So we have different hosts, and you'll notice that the big stacks here in this picture are FPGAs, and I always joke that this is my kind of picture, because the FPGA is 3/4 of the hardware, and the host is kind of disappears into irrelevance, because all you want to do is do all your processing on your FPGA and directly connect that to the network. So once again, each of these FPGAs, it is connected to the host through a PCIe link, but it's also directly connected to the network with 200 gig connections to the top of rack switch. And we're going to be looking at supporting P4 in this framework, but like I said, also supporting fairly large user applications. So the user application that we've played well, so the tutorial, this is from the UDP tutorial, does encrypt and decrypt on the FPGA. So I've got some text from the host, and I can pass it, encrypt it on the FPGA, pass it through the network, and pass it back again. So I can do some round trip. And this is just a tutorial to show you the kinds of things you can do. And the encrypt and decrypt is, in this case, the user logic. It's just a small example to play with these network connections. We also have a tutorial for a much bigger example, which is machine learning. So this is once again showing I've got a large machine learning application split over 2 FPGAs talking to each other directly using a 100 gig switch. So on the bottom, I have what's running on my FPGAs, and they can talk to each other directly. Once again, the development, so developing your neural network model, training, developing your bitstream for FPGA is all done offline in Mass Open Cloud, and then we deploy this at runtime at Cloud Lab. So for the Cloud Lab piece, we're very much interested in, big user applications side by side with P4. For the Fabric piece, the P4 is probably going to be most of what's on the FPGA. So this, something like encrypt and decrypt, might be a better match, where the user-defined piece is going to be an awful lot smaller than it will be in the Cloud Lab setup. So, very similar hardware technology, different use cases in the 2 platforms. So as I said, we're just getting started. That just gives you an outline of the kinds of things we're trying to do. We're looking at P4, both for the fabric hardware, which is the SmartNIC 1000, and for the Alveos. And I'm also very interested in the kinds of application people want to do with P4. So particularly, we're looking at network intrusion detection, in network telemetry, quality of service, and any other applications that people are interested in. And then on the, how do we play with the combination of user logic and supporting P4 side by side on the same FPGA? And one of the motivating examples there is doing machine learning inference. And then, basically the Xilinx solution for P4 is a starting point. We're going to look at other solutions. I'm particularly interested in disaggregation. And what I mean by that is, how do I, make the FPGA basically a first-class citizen on my network? So yes, it's attached to the host, but it doesn't have to be allocated to the user by the host. I can get my data straight off the network. I can do the processing. How do I deal with that whole use case model? So anyway, that was my talk. Once again, the grant is joint with Mike Zink of UMass Amherst. The OCT project involves a ton of other people. We have donations from Xilinx. We're working with all sorts of people, but the OCT stuff works on Cloud Lab and MOC. And I've got some links to some very recent papers. So one's hot off the presses and the other one came out in November. And also we have a GitHub full of tutorials if you're interested in learning more.
All right. Well, thank you very much, Miriam. Again, I encourage everyone to ask questions in the Q&A. So I'll continue on. Junxiao Shi is our next speaker from NIST.
Yes.
Junxiao.
Okay, I will start sharing. Hi, I'm Junxiao Shi from National Institute of Standards and Technology. Today, I'm presenting my proposed experiment of NDN DPDK file transfer. So NDN DPDK is a software implementation of the NDN protocol that the earlier presenter already introduced. But the aim of NDN DPDK is high performance. We achieve performance over 100 gigabits per second. The NDN DPDK code base includes a network forwarder or router and a set of high-speed applications such as traffic jam, data-intensive science community, such as the one working with Large Hadron Collider, because they believe NDN DPDK or NDN architecture, it can simplify and accelerate scientific data distribution thanks to NDN's in-network caching capability. And the NDN DPDK, along with their applications, has been demoed at the recent Supercomputing 21 conference. So the scenario of NDN DPDK file transfer experiment scenario is we want to download the files through an NDN network, and the main metric is the download completion time. So in this diagram, there is an NDN network which has several NDN DPDK forwarders. Each supports in-network caching, and they are interconnected with 10G or 100G links. Then there will be at least one NDN DPDK file server. In NDN terminology, it's called a producer, which has a local...
Junxiao, your slide sharing is stopped.
Oh, I do not know why. I hope it's back now.
Yeah, it's back.
So the experiment we want to do is NDN DPDK file transfer, which is to download, in this scenario, we want to download the files through NDN network and measure download completion time and other metrics. So first we build an NDN network, which could be within Fabric or within other networks, which contains NDN DPDK forwarders with in-network caching, and they are connected with 10 or 100G links. There will be at least one NDN DPDK file server. In NDN terminology, it's called a producer, and it has a local disk, either SSD or HDD. The software will access the disk using the IOU ring API. Then on the other side of the network, there will be a few downloaders that try to fetch file from the file server. That's a basic scenario. before we have Fabric, how we have been doing this experiment, the simplest way is to do it locally. We get 2 or 3 servers, and we connect them with a few cables. We run the programs and collect and analyze logs. We can get a nice diagram of the throughput of the system. But there is a major shortcoming of local experiment, which is the scenario is not realistic. Because the network is too small, logically there are only 3 nodes, and then the latency is close to 0. And sometimes the application or algorithm works fine at 0 latency, but when it's in the real world with higher latency, it does not work well. The other way we tried recently is using a distributed experiment. So our collaborators, they rented 7 servers in different cities on the CERN network, and they are interconnected with internet service providers, so-called layer 2 service, which is Ethernet service, since NDN didn't run over IP, NDN run directly over Ethernet. Then they run the programs and collect and analyze logs. But during the recent trials, there are many issues encountered. First is each location has different hardware. It's causing unexpected errors. And also some links is blocking or corrupting non-IP traffic. And each link can cross multiple service providers. We don't even know who to contact to fix the problems. So eventually during the SC21 demo, only 3 of the 7 servers are usable, and that's not good. If we can have Fabric, there are a few benefits for our experiment. First, Fabric has more hardware than the local development environment. This would allow benchmarking with a larger network. Then Fabric can provide actual wide area latency across locations, since it has multiple locations around the country and the world. Emulating latency locally is possible, but it requires a very large queue that is difficult to do at a high speed. But with Fabric, it comes natural. Then Fabric has more or less the same hardware in each location, at least within the United States. This will reduce unexpected errors caused by running untested hardware. And finally, Fabric is interconnected using dedicated fibers and wavelengths. This ensures non-IP packets will not be affected by the service provider's switches. So this is a sample topology of how the experiment could work, but topology can be designed many different ways. The green nodes are the NDN DPDK forward. We can put 4 of them in different cities on the Fabric network, then interconnect them at layer 2 100G links. The bandwidth could be either dedicated or shared. Both will work. Then some nodes can have NVMe devices serve as local caching, and those devices will need a lot of writes since it's a cache. Then there can be smart NICs which can help with filtering traffic and dispatching within the CPU cores. And also FPGA can also help in this case. We already have collaborators working on the FPGA. Then the producer, which serves, or the file server, will be equipped with either SSD or HDD, and they are connected in some of the locations. Then there can be some consumers or downloaders that fetch file from the producers and through the in-network caching. Then some things we could measure first is the download completion time, especially if we have NDN caching with different caching policies, how does it affect the download completion time? And then the NDN router can react to link failure if we use the Jupyter notebook to introduce a link failure congestion or something. Then NDN routing should be able to react to it, and we should be able to observe from the software logs. Then the packet processing latency within then we can also measure the forwarder's packet processing latency, and this is some specialty that can be easily done on Fabric but not elsewhere, because Fabric switch has we can have some degree of control over Fabric's switch. We can make the switch to mirror the traffic into another port. Then on the other port, we allocate another KVM that runs a traffic analyzer, and combined with PTP timing, we can match ingress and egress packets into and out of NDN DPDK switch, and then calculate precisely the latency. and the results can be streamed in real time to the Fabric measurement infrastructure, so the researchers can see it. Thank you.
Well, thank you very much, Junxiao. So looks like you're pretty ready to deploy.
Yes,
on a
we're
Fabric
waiting for the account.
Okay, that's great. So the next talk will be from Violet from Arizona State University. I believe you'll be presenting together with Abraham from Boston. You're muted still.
Hi, everyone. I'm excited to present our talk on reliability in petabyte scale file transfer. And just in this session, I made some notes about at least 3 or 4 projects that I think our work might impact. So this is joint work with Ibrahim Matta at Boston University, as Casey just introduced, but of course all of the work is being done by the grad students, which here is Arash Sarabi of Arizona State University. All right. So the motivation for our work comes from a lot of these new scientific instruments that are coming online. And in the area of astronomy and cosmology, there are some really big projects coming in the next few years. One is the Vera Rubin Observatory, which is the one on the bottom left. And that one's being constructed as we speak in Chile, to come online probably next year or maybe 2023. And one of the scientific questions they're looking at is the study of dark matter, like what is dark matter and how does its properties affect the formation of stars and galaxies. Another one that is, maybe you've heard about it recently in the news, is the James Webb Space Telescope. So this is the successor to Hubble, and they were trying to deploy it, found a problem, and now the launch date is the 21st of this month, so less than 2 weeks away. And they're also interested in how do galaxies form over time, and stars as well. And yet another instrument that's going to come online, maybe probably more like 2024, is the Square Kilometer Array. And you can see that on the bottom right. They have almost 200 dishes. So this is a radio telescope. It will be the largest one in existence when it gets deployed. And each dish is 15 meters across. And this is being built in South Africa. And in Western Australia, there are more than 130,000 antennas that work with this. And they're also looking far back in time, and they're interested in some of the questions related to, was Einstein right about gravity, for example? I mean, there have been some validation of Einstein's work, of course, but they're looking to do more detailed analysis of curved space-time and deflection of starlight and that sort of thing. Now, for us, what's really interesting is just the size of the data sets that these instruments generate. So on the order of 20 terabits to 2 petabytes generated daily. And all of this data needs to move from the instrument itself over to some supercomputing center for processing, maybe removing some artifacts of some sort, to be archived and then also distributed among researchers. Now, so there's implicitly this, the network is there, right, being used for the file transfer. And there are several file transfer tools. We can see 6 of them here. So these are kind of state-of-the-art file transfer tools. And all of them typically send the data in segments of some sort, most typically over TCP, but some running over UDP. Some of them do error detection at the file level. So in other words, they might use some kind of file compression technique or encryption scheme, checking on the various endpoints. They're often doing error detection over the link layer. They might even use file compression techniques. But I think we all know that all of our error detection mechanisms are not perfect. And as a result, we should be concerned about the probability of undetected errors. And in particular, for some of the data sets that have been mentioned, file transfer needs to be reliable, especially when those files are storing data that capture very rare events. So Rob had mentioned the Large Hadron Collider, which is another huge scientific instrument that we've built. And certainly looking for the Higgs boson is a rare event. And so what we want to make sure is that when files are transferred from one location to another, that errors that may not be detected by the mechanisms in use by the file transfer method don't impact the scientific conclusion or don't propagate. Another example was Alex Feltus mentioned these genomic data sets. And so, you know, what if errors got introduced into the genome sequence or got propagated by accident? Similarly, what if something was detected as a Higgs boson, but was in fact not actually a Higgs boson? So we're interested in ensuring that data that captures rare events, that the likelihood of undetected errors is as reduced as possible. And so we're proposing a multi-layer error detection architecture for this purpose. And the figure here kind of looks like a TCP/IP stack, but don't be fooled by what it looks like. It is a layered, multi-layer architecture, but each layer is defining a scope of error detection. And not only that, the layer is recursively defined and it is parameterized by a policy. So depending on the application needs and also the conditions in the network, we can establish an end-to-end connection that instantiates different policies according to the needs of the application. And it turns out that by thinking of the error detection more generally, we've been able to sort of organize the structure of error detection schemes and generalize the existing techniques within ours. And what the figure on the right is showing is that you can increase the number of layers in your error detection scheme and happen to use smaller or shorter cyclic CRC codes and achieve better results in terms of reducing the probability of undetected errors. And we recently published a paper about sort of the theoretical foundations of our approach. Now, so we're interested in what is the impact of noise on data. And if we go back to our motivating application, what we've been just doing recently is introducing noise into astronomical images. And these ones are stored in what's called a FITS format. And it turns out that point sources, which are stars, have a Gaussian distribution on pixel brightness. And so in talking to our colleagues in space sciences, they said, well, we should introduce Gaussian noise. And so what the figure shows is we introducing Gaussian error into the percentage of pixels. And what the orange line is the original image and how many sources, in other words, how many stars, would something called a source extractor. So something called a source extractor is used to extract what are called catalogs of sources from the astronomical images. And you can see that depending on the percentage of pixels with error, that we could detect far more sources or stars or far fewer than are actually there. And so again, this could impact the conclusions we're drawing, and we don't want that to happen. And so just to show you a different way of viewing the image, so the images are actually really stunning. I really like them. Here they're just in black and white, but on the left is an original image, and on the right is an image where noise has been introduced at 5%, so quite a lot. But we, with our naked eyes, I mean, maybe we could identify some of the sources, some of the stars, but certainly not all of them that are there. And so if we look at what the source extractor is able to find, so it uses machine learning techniques to be able to identify the sources in the images. You can see that the original image had 659 stars, but in the noisy image, there were only 421 of them detected. And so again, there's a potential that we could draw incorrect scientific conclusions if errors are undetected and get propagated in file transfer. And so we're interested to actually, so we've done some of the preliminary work on the theory of our multi-layer error detection architecture, but now we want to actually start to build it and deploy it within the Fabric network. And so initially we're just going to use a static topology, but we think that Fabric has some unique features that we can take advantage of in the implementation of our architecture. And the first is using the measurement framework. So in this way, we can actually query nodes to determine what kind of resources they have, because we're looking for nodes with high compute power. For example, Miriam was just talking about FPGAs. We're interested to implement the CRC computation in FPGAs in parallel. And so we would be interested in finding nodes that have those capabilities. so that we can instantiate the various layers or policies in the layers of our architecture, and also potentially reconfigure the topology if the network conditions were changing. We also think that we'll be able to reduce the delay of file transfer of some of these huge files through pipelining and multipath routing, and that we might be able to take advantage of some of the P4 switches that are available in the architecture as well. And perhaps our file transfer scheme could get implemented in some of the NDN applications that were discussed earlier in this session as well. All right. And so before I end, I just wanted to give a little plug for the workshop that was started by this community. So it stands for Computer and Networking Experimental Research Using Testbeds. And so we would love to see the work that has been discussed here submitted to our workshop. The deadline is, you still have a month. Yeah, more than a month and 2 days. So we would love to see you submit to our workshop. So Ibrahim, did I miss anything?
All right. Well, thank you very much, Violet. This is a long afternoon of many experiments. I felt like there's not a single dull moment going through. It was really surpassing my expectation. I think there's a lot of thoughts and sort of work into that. I feel even more encouraging now that the fabric production site is gradually coming up. More of these experiments can have meaningful implementation now. To start collecting some observations there. So, this is the end of today. Tomorrow, still, we'll continue the federating testbed discussion, but even I'll say more interestingly, there's a community group session where there are 6 topics already identified. Everyone is welcome to choose your own interested topics, and then you are welcome to see any one of them. You can hop around. But one point for the experimenter whiteboarding session, I hope many of those that have not presented today, if you have interesting ideas or you have even questions on whether certain experiments make sense, please do come to the session, even bring some information, and then offer yourself your topic for discussions tomorrow. I think that would be tremendously interesting. So anyone else from the Fabric team, is there something you wanted to bring up? Okay, I suddenly forgot in near me, they don't have a natural way just to say something. So feel free to type if there's anything, but I think this will just conclude the day, and unless Amanda or Brittany, there's something that you want to remind us about.
Yeah, a bunch of the Fabric leadership team is going to be in the lounge at the end of this session. So if you have any questions, we encourage everybody to go to the lounge if you want to network with any of the presenters or any of the Fabric leadership team.